We just talked about a mass falling through the air. Now let's think about a mass falling through a liquid. So say we had a beaker of water here. I always specify water with waves and a fish like that. If we had a mass falling through this water, it would feel a force mg, and it would also feel a resistive force pulling back, r. In this case, though, r is minus b times v, where b is a damping parameter, or is the damping parameter, damping constant, I'm sorry. Okay, and it depends on the properties of the fluid and object. So it's not a simple thing we can calculate. It's a complicated parameter that you usually measure. So what you'll notice is liquid drag is different from air drag. Basically, they're both fluid drags, but this is a fluid drag that is proportional to v, to the velocity. So they're both fluid drags. One is proportional to v squared, the air drag. Fluid is proportional just to v, and that's really just because fluid drags are very complicated, and they depend heavily on the properties of the fluid. So for these, it just goes as minus bv. This is a phrase you will never see. No one calls it the liquid drag. Really, there's air drag, and then this is just called damping. Right? So that's something I made up just to draw the contrast between liquid fluids and gaseous fluids. So using this, we can very simply, again, calculate that terminal velocity. All right, so the terminal velocity happens when what? When the sum of the forces in the y in this case, so we'll say down is in the positive direction, equals 0. All right, terminal velocity means the velocity isn't changing. The velocity isn't changing, the acceleration is 0, so ma is 0. So this occurs when the sum of the forces is 0. Well, one, the drag always opposes what's making it move. So gravity's pulling it down, the drag is the other way. So really this just means that the magnitudes are equal. Since they're opposite direction, their sum is equal to 0. This is really just saying that the magnitude of r equals the magnitude of mg. R equals mg, or you could just say when these forces balance. So if we go with the magnitudes, then this one is just bv. In this case, it's the terminal velocity because we're talking about the specific case, equals mg. So terminal velocity looks much simpler than in the case of air. It's just mg over b. The mass, mg, the force due to gravity divided by the damping constant. There's one thing we can do for liquid drag that we can't do for air drag, and that is we can solve the detailed kinematics. Since it is only proportional to the velocity to the power of 1, we can solve it. So to do that, here's the same drawing. We have this thing. There's basically the free body diagram, two forces. Let's call it the x direction. So positive is down in the x, and Newton's law, right? Sum of the forces equals the mass times the acceleration in the x. All right. What are the forces? mg down minus bv up. mg, we're doing this in one dimension, no need for vector notation. mg minus bv, that's the forces, equals mass times the acceleration in the x. All right, we want to solve that for position or the kinematics. What we have here, actually though, is a differential equation in v. And I've shot all my online classes sideways and backwards and in reverse order, and I've forgotten. This might be your first differential equation. I'm not sure. I've lost track. I apologize. But this is a differential equation in v. Basically, that means we have v showing up by itself and to different derivatives with time in this case. Because, what do we know here? mg is just a constant minus bv. That's the v we're kind of looking for. But this is m, and that is dv dt. So you solve differential equations a lot of different ways. Some of them are shocking. Some of them are straightforward. You would think, well, probably just integrate. And that's what we're going to do here. Sometimes they're easy to integrate. We kind of saw some of these when we're doing kinematics, right? How do you get the position? You integrate the velocity. This one you can integrate, but there's a little bit of a trick. And then some of them you can't even integrate. All right, let's see. But for this one, usually the sort of nice way to write it is to get the derivative by itself. All right, so I'm going to leave this over here. I'm going to divide through by a mass so that I can say dv dt is g minus b over mv. So that's the differential equation we want to deal with. You might think I could integrate it, but I can't. Right? I can integrate this with respect to time, dv dt with respect to time, but I can't integrate v with respect to time because it's a function of time. Right? The velocity is slowing down as it falls through the water, so I don't really know what v is. So what we got to do is rearrange it a certain way, but before we do that, we actually have to do a substitution. Our rearranging won't work unless we substitute first. So let's substitute a new function in, and we'll just call the new function f. And basically, you want to make f equal to this side. F equals g minus b over mv. Okay, this is a technique you learn in calculus and differential equations. I'm sure it has a name. I don't remember all the names anymore. So that's f. Now we take the derivative with respect to time. So we're going to need that, obviously. df dt, the derivative of that constant g with respect to time is 0. Remember, this is a function. This is just the constant acceleration of gravity. It has nothing. So it's minus b over m, and that derivative is dv dt. You could call that a, but we don't want to. We're trying to do everything in terms of v here. So you can use these two substitutions and put them back into here. Right? So we're going to put, let's see, dv dt is negative m over b df dt. Right? We just solved this for dv dt. So minus m over b df dt. That's the right side here, or the left side. And this side is just f, right? Equals f. So we basically took this and we put it there. And now we've kind of simplified it where we can do our tricky little substitution. Let's go ahead and do, though the proper thing is to get the derivative by itself, df dt, bring it back over minus b over mf. Now we can't, still can't integrate it. We can integrate this with respect to time, but f is a function we don't know. We can't integrate it. So we do a trick. We get all the f's on one side and the t's on the other side. That's one of the tricks here. So df over f equals minus b over m, minus b over m dt. Sometimes you can treat derivatives as though they are little algebraic expressions. Sometimes you can't. So what we're going to do now is integrate both sides of this. Right? So integrate from t equals 0 to t. These are technically different t's. Some people call this t prime, right? So t is the independent variable. We're going up to a value of some specific time. I don't like to put on the prime. I find it confuses people more than it helps. And we're going from f initial to f final. And we'll worry about what those are later. Okay, so we're going to do that integral then. So it's the integral of df over f equals minus, I'll pull the constants out, b over m integral dt. So this is from fi to ff. I got ff df over f fi, okay. And bm integral from 0 to t. And the integral of df over f is the natural log of f. And if I apply the limits, it's the natural log of ff minus the natural log of fi, which if you know your natural logs, that's the natural log of the ratio. Right? That's what you get when you integrate and evaluate the limits of that side. And the integral of dt is just the t. Evaluated at t minus 0, this just becomes t. So we didn't mess with a prime in there, minus b over m t. Ah, yes. So it looks like we're going nowhere, but we are going somewhere. To get rid of the natural log, what we do is take the exponent of both e to the x of both sides. So we say basically e to this equals e to that, right? Because e to the natural log of something equals the something. So this means that ff over fi equals e to the minus b over mt. All right? So then you could say, okay, I want to get there quick here. quick way to get there, we go ahead and say, yeah, let's say ff equals fi e to the minus b over mt. But now we got to think, what is ff and fi? Right, these are the initial and final values of this function that we defined here. So let's think, if we drop this from rest, let's say we're drop from rest. So at t equals 0, v equals 0. We're going to drop it from rest. So at the initial time, F initial is gravity is a constant minus, but this is 0. So Fi is just g, just acceleration due to gravity, e to the minus b over mt. F final, though, is g, and this has now reached some value, right? We've gotten up to some velocity that we're looking for. So this is really now just g minus b over mv, right? G minus b over mv. So this really is our answer, but it's in a weird form, right? Because we got, here's our v that we want, and we could isolate it. We want to solve this for v, so we say v equals, let's see, we bring this over here to make it positive, this over here, this becomes negative, and we pull out a g, right? And then we also have to divide, we have to bring the m over b over, m over b, that's got to be there. And then we end up with 1 minus e to the minus b over mt. Looks something like that. Yes, g over b, very good. But we're not even through with that yet, because wait a minute, if we go back all the way and say, what was mg over b? That was the terminal velocity. That's the fastest it's ever going to go. So finally, we get that the velocity as a function of time equals the terminal velocity times this 1 minus e to the minus b over mt. This is really the answer that we were trying to make our way towards. So we now have sort of done the kinematics. What did I say? We have solved the detailed kinematics because we've solved how the velocity evolves in time as you drop something in a liquid. You can't do that with air. You can only do it with fluid or with liquid because this is now something you can actually solve. Well, we just showed how to solve it. If that v were squared, it makes a huge mess. We don't want to deal with it. To get a little intuition for how this goes, oh, thank God this board is clean. You need to definitely in physics learn what 1 minus e to the minus a constant t looks like, because that's a very common thing that comes up. If we were to plot t here and plot our v here, it's really vx, right? And you say at t equals 0, e to the 0 is 1, 1 minus 1 is 0, so sure enough, this should be 0. And if you say it at a very long time, what does this go to? E to the minus big number, minus infinity, is 1 over e to the infinity, so it's 0. So at long times, this goes to 0. So this just becomes vt, or at the terminal velocity, as you would expect, right? So here's velocity axis, there's the terminal velocity, like that. So this does this, basically. It's exponentially approaching the terminal velocity, which is what it should do, which is what the math said it would do. We could, let's see, so this is v is vt, 1 minus e to the minus b over mt. Right? The exponential rate is set by the damping constant and the mass. We could, it'd be kind of fun to take the derivative, right? What if we were to plot the acceleration versus time? Then, let's see, at first it actually is accelerating. There's a slope here, and it's going to 0. Right? So maybe as you would expect, it starts out like this, and the acceleration goes to 0. We could also see that right here. We could take this time derivative. We could say a is dv dt. This is a constant and a constant. That goes away. So you've got a negative sign here with a vt in front. And this derivative makes you pull out a b over m and a negative, which makes that positive, e to the minus b over mt. Right, so there's your acceleration expression. Right, that's a positive. But wait, what is this? This altogether makes g. Right? mg over b is the terminal velocity. So really, says that the acceleration is just the acceleration of gravity, and it exponentially decays, minus b over mt. This is really what you want here. And this makes sense. When you first release the mass in the water, it doesn't have a damping force yet. It's going to accelerate at g. But then that acceleration is going to go down exponentially. And when you're at terminal velocity, the acceleration should be 0. So that's g, 9.8 meters per second squared. So we've done a velocity and acceleration, and you could even do position. You know how to do kinematics. You could integrate to get the change in position based on the area under that curve.